In this lesson today, I am going to go over section 3 for the majority of this section. So I'm still going to break this into two parts, part 1, and then just several more examples will start us off for Thursday's lesson for part 2. Now, what I am going to have you guys work on in class as well is to review for the differentiation gateway exam coming up next week. So what I have right here are 5 problems that I want you to pause the video, work out on your own, and then I'll go over it. So in class, I will be going over several examples as well, but I'll email everybody to make sure you either, if you have the problems printed out, or make sure that you have some of the problems written out for the differentiation review packet. That way you can work on them in class and ask me questions. All right, so if you haven't already done so, go ahead now, pause the video. I'm going to go over these here in a few seconds. Now keep in mind, you just need to show the very first step, the rule that you're applying here, and however you leave it is fine. You do not have to go any further steps to simplify. What I do need you to do, though, is make sure that you write out that we're looking at f prime of x because we're trying to find the derivative. So in number 1, we just want to use the chain rule. So this will become 1/2 times, we still leave the inside stuff the same for right now. So the derivative of the outside stuff becomes 1/2 times this whole quantity to the negative 1/2. Then we multiply it by the derivative of the inside stuff, which will just give us a 6x and then a minus 2. Now in number 2, I actually still had this up here, but you could rewrite it if it helps. And then let's go ahead and find the derivative here. I want to use the quotient rule. So remember, that's low d high minus high d low over low low. It is wrong if you mess up that numerator. So low, which is x to the 1/2 plus 4, we want to keep that in parentheses. The derivative of the numerator becomes a 0. It's just a constant. Minus high, which is 10. D low becomes a 1/2 x to the negative 1/2. And then the derivative of 4 is just 0. And then this is all over low, low, so we could write this as x to the 1/2 plus 4 squared. All right, now for number 3, there's actually 3 factors here, but we're going to use the product rule. I'm going to call this u, v, and w. And we could apply this to just more than 2 factors simply by following the same rule here. Now with the product rule with 2 factors, we just leave one factor alone, we take the derivative of the other. Here we're going to leave 2 factors alone and take the derivative of the third. And we're going to go through this 3 times, and each time 2 factors will stay the same, we'll take the derivative of the third. So here for the first part, I can leave u and v alone. So I'm going to get x squared plus 3 times the quantity x cubed plus 2. But now I want to take the derivative of w, which becomes 5x to the 4th. Plus, now the next combination, I can use or leave u and w alone, but then take the derivative of v. So then I'm going to get x squared plus 3 times x to the 5th plus 1. But now the derivative of v becomes 3x squared. Then I'll do this one more time. I'm going to leave v and w alone, but then I'll take the derivative of u. So here's v, x cubed plus 2. Derivative of w stays the same, x to the 5th plus 1, but now the derivative of u becomes 2x. So applying the product rule to 3 factors is how we want to do this. All right, go ahead and look at 4 and 5. Pause the video, try these on your own. Just a reminder, for something like 4, we could rewrite it this way, and I recommend it. But pause the video to find the derivatives. All right, so for number 4, again, the derivative of the outermost stuff is going to become a 2 times everything else stays the same for right now. Then I want to take the derivative just of sine, so that's going to be times cosine. This inside stuff stays the same. Now I need to take the derivative of the inside stuff, so now the derivative of x is 1. And keep in mind, 1 over x could be written as x to the negative first. So when we go to take the derivative of this, this will become a negative x to the negative 2nd. And it's perfectly fine. We're done. We leave it just like that. In number 5, I'm going to use the quotient rule here as well. Low d high becomes tangent x times 2x minus high d low, so x squared, derivative of tangent x is secant square x, all over low low, so you could write this as tangent x squared or tangent square x. All right, now in section 3.4, we're going to take a look at what we call limits at infinity. And what this is really going to relate to are horizontal asymptotes. But first, let's take a look and review vertical asymptotes. Vertical asymptotes are where a function is undefined, and we get those values by setting the denominator equal to 0. So in this example here, if I have f of x is equal to 5 over x plus 6, because of the domain, I know x cannot be a negative 6. Therefore, there is, I'm going to abbreviate vertical asymptote VA at x equals negative 6. So my graph cannot cross a vertical asymptote. The graph of a function can never ever cross a vertical asymptote. Now horizontal asymptotes are a slightly different story. A horizontal asymptote describes the behavior of the graph at values very far off to the left and far off to the right. So we say it describes the behavior of the graph of a function as x keeps increasing without bound, or as x approaches infinity and or x approaches negative infinity. The graph of a function may cross the horizontal asymptote, abbreviated HA. So limits at infinity and horizontal asymptotes are pretty much the same process. If we find the limits at infinity, we can find the horizontal asymptotes. Or if we have a horizontal asymptote, we can help to find or write out the limits at infinity. So limits at infinity help describe the behavior of the graph of a function as x increases or decreases without bound, and can determine if there is a horizontal asymptote. So a definition here of a horizontal asymptote. The line y equals L is called a horizontal asymptote of the curve y equals f of x if either limit as x approaches infinity or negative infinity, as x increases or decreases without bound, is equal to L. So I have three cases up here. I'm going to call this each blue horizontal line y equals L. Now, as I mentioned before, it is very possible for our graph of the function to cross a horizontal asymptote. So for instance, I can have a graph come up through here, go down, and then right about here it could start to approach it. So it is, and it usually crosses somewhere where the x values are small, but as x is approaching infinity or increases without bound, this line right here, this curve right here, is going to just keep heading out this way. So as that horizontal line continues on to the left, our curve is getting closer and closer to it. For our second example, so in our first case, it did cross here. This one may not cross at all, but typically what we're used to seeing is that it's going to approach it. So again, as x keeps increasing without bound. Now, I could have very well have drawn this off to the left, but in this case, I'm just using as x increases without bound. So here's an example where it doesn't cross the horizontal asymptote at all, but we could still see as x keeps increasing without bound, our graph is getting closer and closer to that horizontal asymptote. And third, it can start out, our graph can start out as sort of a function that's sort of oscillating, but as we keep, so it's crossing it many times, but as x keeps increasing without bound, it's getting closer and closer to that. So again, we can say as x keeps increasing without bound, our y values are getting closer to this horizontal line y equals L. Now here's a theorem that we are going to use to help us find different limits at infinity. And what's really important is this limit notation. So if r is greater than 0, so if we're looking at any positive rational number, then the limit of 1 over x to the r as x keeps increasing without bound is equal to 0. We've done this in the past when we've looked at like 1 over a very large positive number or 1 over a very large negative number. This is going to give us 1 over a very large positive number, which pretty much means it's a very small number altogether. So this is going to be 0. And then here, we just want to make sure if our limit as x is approaching negative infinity or x keeps decreasing without bound, it's still going to give us the same thing. But it's saying if r is a positive rational number such that x to the r is defined for all values of x, then the limit as 1 over x to the r of 1 over x to the r as x keeps decreasing without bound is going to equal 0. This just gives us 1 over a very large negative number, which is still practically 0. Except this one is approaching 0 from the right, or from above rather, So we're looking still at positive numbers. These are going to be negative numbers, but they're going to be very, very small negative numbers. So we say we're approaching 0 from below, but it's still 0. All right, so we're going to explore this here just by using a table and then look at the graph as well. So here I have the limit of 1 over x squared, and this is that same format of 1 over x to the r as x increases without bounds. So I just made a table of some values here. Notice my x keeps increasing rather quickly here. So I want to write this out, 1 over x squared. So this will become a 1 over 1, which is just 1. Next, I'm going to get a 1 over 100 squared, which will give me 1 over 10,000. Next, I'm going to have 1 over 1,000 squared, which is 1 over 1,000,000. And then 1 over 10,000 squared gives me 1 over 100 million. And you can just type that on the calculator just to see. But notice these numbers, if I were to turn them into decimals, I'm going to get a point and a ton of zeros with a 1 here. So we could write that the limit of 1 over x squared as x increases without bound is practically 0. Now over here, because my denominator is squared, it's x squared, when I square a negative, I'm still going to get the same thing. So if I have -1, -100, -1,000, -10,000, I'm still going to get a positive 1. I'm going to get a 1 over 10,000 because a -100 squared is still positive. I'm going to get a 1 over 1,000,000, and I'm going to get a 1 over 100 million. So this limit is the same. As x keeps decreasing without bound, 1 over x squared is still going to equal 0. So the graph of this, as my x's are very close to 0, what's going to happen is on the right side, I'm going to get something that looks like this. Now this is an even function because for any x value I substitute in here, the opposite will still give me the same. So this is what it looks like on the other side. That's symmetry. So this is y equals 1 over x squared. And we could see this now as x keeps increasing without bound. We're approaching the horizontal asymptote of y equals 0. And this is as x keeps decreasing without bound. The same thing is happening here. So we have a horizontal asymptote at y equals 0. Now this was 1 over x squared. Let's take a look at 1 over x cubed. And I went ahead and just filled out the tables for you here just to note when we cube a negative, we're just going to get the opposite. So this is actually an odd function, but pause the video to copy this down. So with this being an odd function, we're actually going to have symmetry with respect to the origin. So as x is approaching infinity, or it keeps increasing without bound, I'm still going to have the same graph, but we're going to get to 0 a lot quicker. So it might start to look like this. So that still stay the same as 1 over x squared. But now over here, so we're going to say the limit of 1 over x cubed as x increases without bound is still going to be 0, but it's going to get to 0 a lot quicker. Over here, and notice it's approaching 0 from the top, so I'm going to put a little plus sign here. Now it's not necessary for you to do that. I'm just kind of indicating the slight differences here of why they're still equal to 0. But as x keeps decreasing without bound of 1 over x cubed, now we're going to have it start to look like this. So these are still going to be very small negative numbers. So it's still going to equal 0, but notice we're approaching 0 from below. So we're going to have that little minus sign there. So this is what the graph of y equals 1 over x cubed looks like. We still have a horizontal asymptote at y equals 0. It's just where our graph is on different sides of that horizontal asymptote. All right, so we're going to use that idea. We're not always going to continue to make tables here. We're going to find the limit, though. We're going to use that big idea to help us find the limit if it exists. If not, we're going to write DNE does not exist. Here's a little trick, though. To help us determine that, to evaluate the limit at infinity, first divide both the numerator and denominator by the highest power of x that occurs in the denominator. So take your time, pause the video to copy down these directions and that the process here, and then we'll take a look at number 1. All right, so what this process is saying, we still need to keep the limit notation. Now in Calc 2, there's going to be some other methods that we get into, especially when we encounter what we call indeterminate form. So if we try direct substitution and we get 0 over 0 or infinity over infinity. So there's another nice little hint with limits that will be brought back up in Calc 2. All right, so again, following this rule, I want to go through everything. My highest power in my denominator is x squared, so I want to divide everything in here by x squared. So this is how I'm going to write it. But in order for me to better see that rule, that theorem, I need to simplify this. So yes, this is going to require some work. So simplifying this now, 5x squared over x squared is just 5. I can leave, I have to leave, I have no other choice, 1 over x squared. Likewise for 4 over x squared, but now I'm going to get a minus 3. So now what we have are these little fractions. As x keeps increasing without bound, this fraction here is going to follow what we just saw here. It's going to go to 0. Same thing here, this is going to go to 0. What are we left with now? Just numbers here. So if I take the limit of a constant, I'm just going to get that constant of negative 5/3. Now take a look here. The degree in the numerator happened to match the degree in the denominator, so maybe that's a very important observation to make. Let's go through for number 2. Pause the video to copy that down. We're going to do the same thing here. I'm going to go through and divide everything by x cubed because that's my largest power of x in my denominator. So we're going to have x cubed over x cubed minus 4x squared over x cubed plus 5 over x cubed, and then 4x cubed divided by x cubed. Everything here gets divided by that. And then we'll simplify in the next step. And again, it's important to keep rewriting that limit notation. All right, so x cubed over x cubed, that's a 1. Then I'm going to get, if I simplify this middle fraction, I'm going to get a 4 over x, and then 5 over x cubed stays the same. In my denominator, my first term is just going to be a 4. Next, I'm going to have a minus 1 over x, and then plus 1 over x cubed. So the same idea, as x keeps increasing without bound, any fraction that has a power of x in the denominator is going to become very small, practically 0. And again, I'm left with the constant here. The limit of 1/4 is going to be 1/4. Now, again, if you notice, the degrees are the same, so that's going to be a trend, but you still need to show this work. All right, let's take a look at 3. Now, if you notice in 3, the degrees are not the same, so let's see what happens here. I still want to go through the same process, only now x is approaching negative infinity. My largest power of x is x to the 4th, so we're going to have 7x squared divided by x to the 4th plus 2x over x to the 4th. On the bottom, x to the 4th divided by itself, and then 1 over x to the 4th. So again, I still want to simplify this. So I'm going to get a 7 over x squared plus a 2 over x cubed. Then this first denominator term is going to give me a 1 plus 1 over x to the 4th. So again, everything that has a fraction, 7 over x squared, as the limit as x is approaching either plus or minus infinity, this is still going to go to 0. This is still going to go to 0. This is still going to go to 0. So what happens here is we technically, yes, have a 0 in our numerator, but it's getting closer and closer to 0. So if we have 0 divided by anything, or a very small number that keeps getting smaller and smaller divided by anything, it's still going to be a very small number. So we're going to get a 0 here. Okay, very similar for number 4. Let's go through the same process. Pause the video to copy that down. And then we just want to divide everything by the largest power of x in the denominator. So in this case, it's going to be x squared. So I'm going to go through and say 2x cubed over x squared, and then 5x squared over x squared, plus x over x squared. And then we want to simplify this. So up top, I'm going to get a 2x. In my denominator, I'm going to get a 5 plus 1 over x. So as x keeps increasing without bound, the only fraction I have here, that's going to go to 0. Now what's going to happen? I'm left with a 2x. So just to write this, the limit as x approaches infinity. If I have 2x over 5, that's the same thing as saying 2/5 x. So as x keeps increasing without bound, 2/5 times x is going to keep increasing without bound. So this keeps taking off, and gets very large. So we're going to actually have an infinity here. All right, 5 is a little different. We've seen this before with other limit problems, and anytime we saw a square root, we tried to rationalize that. So that's what we're going to do here. So please go ahead and copy this down. I'm going to treat it like a fraction, so I do want to put it over 1 because now I want to rationalize this in order to apply that property or that theorem. So it's going to be square root of 4x squared minus 1 plus 2x, top and bottom gets multiplied by this. So as I rationalize my numerator, I'm just going to get a 4x squared minus 1. Outside and inside terms cancel, then I'm going to get a minus 4x squared all over that denominator. Now if you notice in the numerator, 4x squares cancel, and I'm left with a negative 1 over square root of 4x squared minus 1 plus 2x. Now technically I have a number, a constant, over some kind of variable. Now if I keep increasing my x's without bound, this denominator is going to keep increasing itself. Notice I don't have any fractions here, so this is going to become negative 1 over a very large positive number, which is practically 0. All right, just a few more we're going to go through here. Now here we kind of have to do a little substitution step. Let's imagine, let's just set another variable here, t equal to 2 over x. So now this becomes the limit as x approaches infinity of sine of t. And what this can allow us to do, if we go back down to t is equal to 2 over x, we could say as x increases without bound, t is getting smaller and smaller, so t goes to 0. So technically what we could do, instead of keeping the infinity here, if I'm going to substitute the t in, I'm going to replace it with the t is going to 0. And then we could do direct substitution here. Sine of 0 is just going to be 0. So we did a little manipulation right here, but I had to change this part right here if I'm going to substitute the t in. So first we let t equal 2 over x, and then we just looked at this and said, well, x is approaching infinity, this is going to 0, and sine of 0 is 0. Now let's just take a look at the limit of cosine x as x keeps decreasing without bound. What I want you to do for this is to picture the graph of cosine x, y equals cosine x. Would you think that there were any horizontal asymptotes to this function? Because isn't it just a wave function? So it's not flattening out anywhere. In fact, as x keeps decreasing without bound, no matter where we're at on the graph, doesn't y equal cosine x just keep going up and down in between 1 and negative 1? So for either end that we were looking at, in this case we're just looking at x is decreasing without bound, the values of cosine x just keep going back and forth, so we say it oscillates. So the values of cosine x oscillate between 1 and negative 1 infinitely often, so they do not approach any definite number. So the values of cosine x oscillate between y equals 1 and y equals negative 1 infinitely often. So if we just have y equals cosine x here, so they do not approach any definite number. Therefore, the limit of cosine x as x decreases without bound does not exist. All All right, and then our last example for this part, we're going to take a look at the limit of sine of 2x over x as x increases without bound. What we could do with this one is first separate it, the limit as x approaches infinity, using the limit laws. We could show that this becomes 1 over x times sine of 2 over x. And then separate this once more into individual limits. Now, didn't we just find this one on the previous page? And we said that that was what? Didn't that come out to be 0? Now this one, this just becomes 1 over a very large positive number, which is also practically 0. So 0 times 0 gives us 0. All right, so I'm going to end this lesson here for today. Like I said, I'm going to just go over some more differentiation practice problems for my students in class on Tuesday, and then I'll pick back up. We'll do several more examples here and start section 3.5, summary of curve sketching, on Thursday with some more review for the differentiation gateway exam. So as always, guys, take care and let me know if you have any questions.